Okay, let's start today's session. Good afternoon, everyone. Welcome back to the second class of doubt clearing of this MM40 aluminum-based metal alloys and metal matrix composite class. The previous class recording has already been uploaded in the YouTube. You guys will be communicated through your email. You'll get the link and the PPTs. For previous class, there is no PPT or study material. For today's class, I have made one study material. I'll share that. And also today's class recording will also be shared and uploaded in a YouTube, and the links will be shared with you all. So let's start today's class. Before that, if you have any doubt from today's this week lectures, please let me know. Otherwise, I'll start sharing my PPT. Anyone? Do you have any doubts? No? Okay. Then I can start sharing my PPT. So here is a small presentation. So first of all is from previous week we had some doubt. So I'll first try to clear your doubts from previous week assignments, and then we'll complete the previous year assignment for week 2, and we'll discuss about the topics elaborately of week 2 lectures. So first is we got to know about different aluminum alloys, wrought alloys and cast alloys, their grades, and how they are different from one each other is mainly because of the alloying elements. So these are the grades 1 to 7000. 1000 series means those are wrought alloys, and depending upon the main alloying elements, these grades are named. And among these 7 grades, 2, 6, 7 and 8 are heat treatable alloys. So as I said in my last lecture, I'll share some example of the different alloys so that you can understand. So let's start. So yeah, first we have 2024 and 2014 alloy. So 2000 series means the main alloying element is copper. Here you can see these the applications I have noted down. So I have noted the applications from mainly aerospace engineering. In aerospace, aluminum alloys are broadly used, so that's why I have picked this aerospace application for aluminum alloys. So different grades of alloys are used for different applications because of their different properties, and these properties are determined by the main and the consecutive alloying elements and their percentage. How this 2024 is used for its high yield strength, high grade alloy with excellent fatigue resistance, commonly used in sheet form for the wings and fuselage. Then this 2014 is the second most used aluminum alloy in this industry of aerospace. High strength toughness is its properties, but it is more susceptible to corrosion. Anyhow, anyway, used inside the framework rather than the shell because of this corrosion resistance property, this low corrosion resistance property of this 2014 alloy, but also it's suitable for arc welding. The composition, if you see, the copper is the main alloying element, which is more in percentage. So in 2024, 4.3 to 4.5% copper is present. Also, there is a range of each alloy. It doesn't mean that 2024 alloy will have a definite percentage of each element. So according to our properties, when we go for using any aluminum alloys for a particular application, we choose the alloying element percentage in that way what we want. So the copper is the main element here. In 2014 also 3.9 to 5% copper is present. So next is 5052 and 6061. So for 5052 the main alloying element is magnesium for 5000 grades. But for 6000 grade, the main alloying elements are magnesium and silicon. So you can see the percentage of magnesium and silicon is higher in case of 6061 than other elements like copper, zinc. And also always remember, all the types of alloying elements are present inside all the aluminum alloys. Means the more commonly used alloying elements like magnesium, chromium, copper, silicon, manganese, zinc, but it's about what percentage they are being used. According to that, these classifications of 1000 series are there. So their application is also written. I'll share this PPT with you all so that you can see what are the applications. It's not important for this class, that's why I'm just skipping that applications. Next is 7000 series. So in 7000 series, zinc is the main constituent elements. So according to that, and for that, the percentage of zinc is pretty much higher in case of both the alloys. You can see 7 to 8% in 7068, and for 7050 it's 5 to 6%. It it's pretty much higher. And and for high corrosion resistance, strength, these that properties, applications in different and specific applications, they are used in aerospace engineering. Other than aerospace also, in other industries like for automobile industry also they are being used. Also these were the main aluminum alloys which are used. Other than that, this 2219, 6060, 7475, these alloys are also used, but comparatively they are less commonly used in aerospace engineering. So this was about the recap about week 1 lecture series. As I said, I'll show microstructure of few alloys as well. So here you can see from a paper I have taken this data. I have put the reference, you can check later as well. In a particular aluminum alloy, so if we are mixing titanium or boron, what they do is, here you can see titanium or boron are used to refine the primary aluminum grains. So when you refine the grains, means always remember, when the grain size is decreased means the strength is increased. So they are refining the grains because aluminum, pure aluminum is having a lot of ductility. It's a ductile material. So the strength of pure aluminum is not that much. So to use the aluminum for different applications, we have to have a bare minimum strength in it. So that's why we go for different strengthening. And this is how, by using or mixing different constituent elements, we can enhance the strength or hardness of aluminium. So titanium and boron is refining the grains. In also TiAl3 is a compound. Whenever you process aluminum or aluminum alloys with high temperature with titanium, the titanium is having a lot of affinity towards this aluminum and will form the TiAl6 or TiAl3, and it will serve as a nucleate site for the primary aluminum and will form this dendritic structures, which will again enhance the strength. The next is this one. Different types of this silicons were used and mixed in this particular alloy to enhance the microstructural properties, to get some properties which are needed for a specific applications. So here you can see for different microstructure, the microstructure arrangement is changing with different silicon percentage. Similarly, here also you can see similar things. Manganese and combination of chromium and manganese were mixed, and the results were like some difference in the microstructure. Aluminium doesn't have any phases, barely has phases like austenitic. Like we have austenitic steel, martensite steel, so martensite, pearlite, austenite we have in steels. Those type of phases are not there in aluminium, which is a great advantage for the researchers, because we don't have to worry about the phases much. We have to just change the microstructure anyhow to just strengthen the aluminum. This is why I would say the strengthening of aluminum is pretty much easier than strengthening of those type of steels, but still it's difficult for us who are working in aluminum alloys. Anyway, these are some more literature review. So iron leads to the formation of complex intermetallic phases during solidification, and these intermetallic phases, always remember, if the material is ductile, like aluminum is ductile, but if anyhow we can make an intermetallic formation inside the metals, it will obviously act like a brittle site or strengthens site for that particular metal. So if we want to go for strengthening or hardening, we can go for this formation of intermetallics inside that ductile metal or metal alloys. So this was all about the recap about week 1. Uh, if you don't have any doubt, we can go to the week 2 doubt clearing session. So, okay, I'll go to the week 2 topics. We'll discuss about it, and then if you have any particular doubt, you just tell me, we'll discuss. So week 2 topics were first the modifying element using this IIT impurity induced theorem. Next we learned about the solution hardening, and using 4 different methods we learned about the solution hardening like elastic interaction, modulus interaction, stacking faults and electrical interactions. Then we got to know about the atmosphere, or we can say due to the different short ranging ordering, then clustering, long range, then superlattice, these things, then antiphase bonding, we got to know about the atmosphere, what is that. And then we went to the yield point phenomena, where the stress strain curve was drawn, and why that upper hill point and lower hill point is got that was shown. After that, strain aging and a little bit of Cottrell-Wilby theory. So if you have any specific doubt, please let me know so that we can discuss upon that.
Excuse me, ma'am.
Yes.
Ma'am, actually, I had a doubt in the IIT theory and like the other one. There were two theories that were discussed. I am not able to understand the difference between the two. Like in both, you're adding modifiers. They in both, it's getting attached on the plane in which the growth is taking place and trying to stop the growth. But I don't understand the difference between the two.
Okay, no problem. So in last class, if you remember, I had shown that, yeah, so there is a silicon growth inside that aluminum silicon alloys. If silicon is anyhow present inside aluminum alloys, it will always try to grow inside it. And as I said, due to the valence shell present inside silicon atom, so silicon has always has a tendency to spread its arms and have a mesh like structure, and due to which silicon atoms and its growth induces different kinds of brittlety inside a particular metal. So if there is a atomic structure where there is a twinning effect, which is meant like if there is a particular plane or direction, and if it's 211 plane direction, and silicon has a property like towards that direction, if it is having similar type of structure in both the sides, it will start grow or growing from that particular direction. So it will be like a staircase like effect. It will start growing like this, and this is how this is its side looks. And if this growth is increasing with time, then it will induce a lot of brittlety inside that particular metal. And as we are using aluminum alloys, aluminum is a ductile material, so we anyhow don't want any brittlety or this type of brittlety inside aluminum alloys, because if we are using aluminum alloys, then definitely we are using aluminum alloys for its inherent properties like its ductility. We can strengthen, but we don't want any brittlety. So to restrict that, IIT says that you mix some kind of or modifiers which will restrict this growth. Understand this thing, this growth cannot be restricted, but what we can do is, if we can break the chain, like if this growth is growing like this, and if somehow we can do from this to this, because wherever there is a primary silicon it will grow, but if we can somehow break the chain, the brittlety will not be that much, because inside a particular aluminum alloy, this is the primary aluminum, and if there was a small silicon, primary silicon, which has grown like this, and now it is having a lot of brittlety and introducing a lot of brittlety inside the metal. If we can go from this to this, where there will be small silicon growth inside the whole metal alloy, it will be beneficial for us. So what we do is, adding some modifiers, we are just changing the growth site. We are adding modifiers like strontium, barium, sodium. This atoms, what they do is they get attached to the silicon which is growing, and from if there is a grow in that silicon, growth like this, and from after few times, after few seconds, if the strontium has been attached to that particular atom, silicon atom, and now silicon cannot grow farther because the strontium has been attached with the silicon. So what will happen that uh, from the other primary silicons which are present inside the metal, there the growth will start. If the other strontium atom comes and attached to that, then other primary silicon which is present inside the metal, that will start growing. So this is how we can restrict the silicon growth in a particular way. We cannot stop the silicon growth. Silicon will grow anyhow, but we are just changing the sites so that continuous growth will not occur. And this is what IIT says. But for next theory, which is like aluminum, if there is a aluminum and silicon alloys, if we melt it, it will stop, like aluminum is having more thermal conductivity, whereas it is also having less latent heat of fusion. So as a result, if we melt the aluminum metal, and if anyhow the aluminum and silicon both are melted, what happens is aluminum will solidify faster because of its properties like high thermal conductivity. If aluminum is solidified faster, so if there was a primary silicon and there was a aluminum growth, it will be like it will solidify faster and it will trap the silicon present inside it. And this is what, it's not like adding any modifiers, but yeah, we can add any modifiers to make this solidification even faster. But this is a normal habit of aluminium, that it will solidify faster, and we can even increase the speed of this solidification by adding some modifiers. There the modifiers were playing the important role to change the growth side of silicon. Here they are just helping to solidify, or helping the aluminium atom to solidify faster.
Ma'am, actually, there was one more theory that was discussed, like the restricted growth theory or some TPRE theory. It was like the second one. So,
Okay, wait.
ma'am, like I wanted to ask that I understood that in IIT they are adding these modifiers are getting attached to some kink or some places which are uneven. But over there in the TPRE theory, it was said that it is getting attached to that particular plane, like you just said now that, like in that plane. So, I don't understand how getting
No,
attached to.
TPRE is not a theory. TPRE is twin plane return edge. The edge or the direction through which this starts, that edge is calling the plane return edge. Wherever that TPRE is found, from there, that is a stable site. So from there, that growth will start. And using modifiers, we can restrict that growth. It's not another theory, it's like similar thing, we are just adding modifiers to change the growth side, as simple as it.
Okay, okay, I understood. Thank you, ma'am.
Any other doubt from week 2? Anyone? No. Okay, so then we can just start discussing the previous year assignment. Okay, so you guys can just unmute yourself and tell me the answers. These are the previous year assignment from week 2. Uh, so which of the following designation is used to notify wrought aluminium alloy with Cu as a major alloying element? Anyone? You guys know the answer, right? You can just unmute yourself and tell me. No?
It's the second one.
Yes, it's the 2000 series. Next is, what does the second digit in wrought alloy designation indicate? Is it purity level, major alloying element, variation in specific alloy, or does it have any significant meaning? It's also there. You can answer. It's good if you guys interact with me during this session.
Purity, purity level.
Okay, purity level, no. The second digit. Wrought alloys are like 1000 if it's, then this one is the purest aluminium, and sometimes this double x, the last two digits are used to indicate the purity level, like 99 point something percentage, but the second digit in wrought alloys,
It does not have a significant meaning.
no, it has a meaning.
It should be variation in specific alloy.
Yes, it defines the variation in specific alloy. So next one is, what do the zero? Yes.
Ma'am, could you please elaborate on that? Like, I didn't get that. Like, what variations are
It's
there?
not like variation in specific alloy means it's not like if you are mixing like in 2000 series it's a copper alloy, and if in 2014 you are mixing somewhat around point or 1.2% copper, it's not like that 1.2% will be written over here, but it will show us some digit. If you go in the deep of that number, you'll see how many specific alloying elements are present. It's not like it will define two like 2% carbon or two like two main elements. It's not like that. It's just it defines the variation in specific alloys, like what are all other alloying elements are mixed in what percentage, and seeing that and with varying with the data sheet available for aluminum alloy, you'll get to know what all elements are present there and with different percentage, and also either they are heat treatable or not, or what will be the precipitate if they are heat treatable.
Okay, ma'am.
What do the 0 and 1 after decimal point indicate in cast alloy designation? This thing was discussed in the last class as well if you have attended. Anyone?
It is a finished casting and ingot respectively.
Sure?
Yes, ma'am.
Yeah. Okay. So don't mess with this first two options. So 0 is finished casting and 1 is it will go for another post process or secondary processes. Then which of the following aluminum alloys are or is heat treatable? You guys have the answers in your copy. You must have written. It's welcome.
It is a
Yes.
2000 series, 3000 series, and 6000 series. Is a heat treatable.
3000 is not heat treatable. The rest are heat treatable. Means 2, 6 and 7. And also 8000 which is not present in the option, but 3000 is not heat treatable. Anyway, no problem. The next question is which of the following statements is or are correct in case of aluminum alloys designated as AA 7000? It's 7000 series. So what is the main constituent element?
Zinc.
Zinc. So it
Zinc.
contains zinc as a major. Is there any other things which seems to be correct? Is it heat treatable?
Yes.
Yes, yes, yes.
It's heat treatable. So if it's heat treatable, so can we go for the precipitation hardening?
Yeah, it forms precipitates.
Okay. But it's saying it doesn't form precipitate when subjected to heat treatment. Okay, no problem. This answer was given there, but I also think that there will be some precipitate when it's subjected to heat treatment. But let's see. Okay, no problem. Addition of silicon as an alloying element is useful for casting of aluminum alloys because
Because silicon improves the fluidity of aluminum mass, and silicon reduces the solidification shrinkage in the casting.
okay, and also it reduces the melting temperature of aluminum. Okay, next is when aluminum 7Si alloys are cooled from 700 degrees centigrade to the room temperature, then its microstructure will contain following phases. Okay, this was not taught, so it's primary alpha aluminum and eutectic silicon. Okay. Next, the phase responsible for low ductile or ductility in hyper-eutectic aluminum silicon alloy is, this is very common answer.
Primary alpha aluminum.
Uh, is it alpha?
He said primary silicon.
It's due to the primary silicon particles.
Yes. That's
Okay. So next question is, which of the following statements are correct regarding modification of aluminum silicon alloy by addition of small amount of chemical modifiers? देखते हैं.
The first, second, and I guess the third also.
Only the first second. The chemical modifiers deactivate the TPRE mechanism. As I said, na, the TPRE is not a theory. TPRE is a site which is preferable site for a silicon to growth. So chemical modifiers, if you are mixing, so it will just deactivate means it will change the growth site, and also it absorbs on surface and prevent the attachment of silicon atom to the crystal.
Now, doesn't it also promote grain refinement?
Grain refinement. We cannot say that it's promoting grain refinement, because it's not doing anything to the aluminium present over here. It's only reacting or interacting with the silicon present over there, so we cannot say that. But mixing some other elements can promote the grain refinement along with the chemical modifiers. It can happen.
Okay, now.
So the next one is on cooling of aluminum silicon alloy with higher cooling rate during its solidification. What will happen?
ductility of aluminum alloy decreases as well as morphology of eutectic silicon changes from coarse needle to fibrous fibrous form.
Hmm. So, but the ductility increases. I think you said decreases.
Ductility is decreases, ma'am.
Uh,
I
देखो,
think
if
so.
the cooling rate is very high, na, then the
Yes.
aluminium, if the cooling rate is slow, aluminium will get enough time to get solidified, and will, in case the silicon present over there, so thus we can say it's restricting the growth of the silicon. But if the cooling rate is very high, there will not be any precipitate, or there will not be any time for the aluminium to grow that much. So if the cooling rate is very high, जैसे था वैसे ही freeze हो जाएगा. So it's like it will not affect the ductility much, we can say. It will not decrease the ductility because the aluminium will not get enough time to encase the silicon and those things, but it will not affect the ductility much.
Okay.
And as you said, morphology of eutectic silicon changes from coarse needle to fine fibrous form. So yeah, this was all about the previous year assignments. So now we can start discussing about the topic of this week, which are first starting from this. But if you have any specific doubt, we can discuss after that. Anything to say? I feel that this week lectures were pretty much tougher and complex than the previous week lectures?
Yes, yes, madam. Sure.
Yes, so if you have any doubt, anything you want me to discuss about, we can do that.
Ma'am, actually, it's not directly related to the lecture, but I wanted to know more on Berger vectors.
Okay, Berger vectors. Berger vectors is something like in the direction where the dislocations, movement, and the sleep direction is like interacting. Like if the that is a age dislocation. Wait. So it if it is a age dislocation, you'll find that the Berger vector will have something like a perpendicular relation with the sleep direction. If this is the Berger vector and this is the sleep direction is like where the sleep will occur, but Berger vector is defining us that how the dislocations will move through the sleep and how they will interfere and what type of dislocation will take place. Because for age dislocation this will be the direction for sleep, but for screw dislocation I cannot draw the screw dislocation, but it's something like there will be an extra plane or extra portion from which through the helical or spiral path the dislocation may take place. So there the slip direction and the Berger vector direction is in parallel. If you want me to discuss Berger vector, we can discuss over this topic. मतलब 1 घंटे का क्लास तो ले ही सकते हैं. Berger vector is that much important for the slip direction, dislocation, these things. So अभी के लिए just remember or just try to understand that this Berger vector is very important if you are talking about the dislocations, like how the dislocation will move, which is the sleep plane for different dislocations or defects. Dislocations are nothing but defects. So for different types of defects, the sleep direction and the defect direction is different. So there is a small relation between these things, and that relation is defined by this Berger vector.
Okay, ma'am. I'll try to go through this from my end also, thoda sa.
If you want, I can discuss it from the next class, but I don't feel I'll get enough time because the next class is also going to be very tough and complex.
Ma'am, otherwise, can you give me some sort of reference from which I can go through
Yeah,
this?
yeah, I can do that. I'll find
Yeah.
some easy references in which you can clearly understand, or I can make some PPT on Berger vector. You will understand from that.
Ma'am, sure.
Because this
Thank you.
PPT and this recordings are shared with you guys, na?
I am not quite sure, ma'am. I didn't get it for the last lecture.
Okay, actually, I have uploaded it a bit later, so you'll get that. You'll get the access. You will be
Sure, ma'am.
studying. Any topic from this you want me to discuss? No? Because today I cannot go through one by one each topic because these topics are very large and complex and will take a lot of time to go through. So that's why I want any specific things that, on which we can discuss. So okay, should I ask question to you? Can anyone?
Ma'am, actually one doubt, and I just wanted to ask about the energy gradient and like the equipotential surfaces. Can you please explain that a bit?
Okay. Huh. So first of all, always remember if we are talking about a particular metal or a particular structure, here we are talking about the aluminum metals. There is always the dislocations present inside the metal alloys. It will always try to move inside the metal alloys, and if the dislocations move, the ductility, it symbolizes the ductility inside the material. If we are providing or giving a lot of force or stress in that particular material of that metal alloy, the dislocations will start moving, and the ductility will be enhanced and it will show the ductility. But anyhow, it cannot help us in every type of applications. In different aerospace and industrial applications, we need more strength, or strength more than ductility. So to enhance the strength and the hardness, because strength will come if we are in if we introduce some hardness in a ductile material, so that strength will serve the purpose to restrict the force, or the restrict the result of the force that is happening inside the metal alloy. So this is why we are always trying to restrict the dislocation movement by introducing different techniques. There are four techniques. So we are basically knowing about the solution hardening, how we are hardening the metal to restrict the dislocations. So as you said, equipotential line. So before coming to that, equipotential line came into the picture while we were talking about the yield point phenomena or strain aging. So what happens is, when we are talking about strain aging, so in normal heat treatment also there is one process which is called aging. So we'll rise the temperature of that particular alloy, and then we'll hold that for a particular time interval. And at the holding time, what happens is called aging. That time is definite hours or days. We keep the or hold the material at that particular temperature, and in aging this sort of mechanisms happen, in which the strains are induced, and due to which we are restricting the dislocations movement. So what happens is, if we draw the stress strain curve, it's more looks like this. So here there are few yield points, upper yield point and lower yield point. So you want me to discuss the equipotential line only, or strain aging also?
Not actually, I got strain edging a little bit, but I wanted more on equipotential. But if it's
Okay, okay, no
how
problem.
it moves, right?
So it's like whenever the solute atoms are interfering with the dislocations, there is a strain working in between these two things. As you can see here. हाँ, इधर पे देख सकते हो. So when the solute atom is present or introduced inside a particular atom, it will introduce some compression and tension or some shear stress inside that metal alloy, and it will result in some strain inside that particular alloy. So it's nothing but the compression, tension and the shear is nothing but the result of the interaction between the solute atoms and the dislocations. Dislocations also try to move, and solute atoms just try to catch up the dislocations, because dislocations move like this. If this is a dislocation, suppose this will move like this, following a particular path. But if this is a solute atom which is trying to catch up this dislocation, it will move like jumping from one position to a vacant position nearby. When it has jumped, so it will be like this, then it will again try to jump in a nearby vacant position. So it takes more time to move than a dislocation. What happens is, there will be an interacting or interfering stress working in between this solute atom and the dislocation. So there will be an energy whenever we are adding some or rising the temperature. This temperature is a favorable condition for both these things to move faster. Whenever we rise the temperature, this dislocation will move faster, and this thing will also increase its speed, like this jumping from one position to another nearby vacant position. And what happens is second phase precipitate forms, or the atmosphere is formed. But if we are talking about the energy between the dislocation and solute, which is given by U, which is A sine theta R. We are denoting, like, if this is a slip plane, this is a solute atom present over here. So this will be the dislocation movement, and that will be theta angle from the slip plane, and the equation will be like this U is the energy, or interaction energy between dislocation and the solute atoms. So equipotential lines are nothing but some giving us some favorable conditions, or defining the path of the dislocation or the solute atoms to move. We are saying that this interacting energy or interfering energy is highest at the smaller circles, and however, as this circle increases its diameter, radius, the energy is decreasing. So it's also okay, because after that, also the, what say, this plane movement can be in both directions, so plus minus both type of circles are there. So why they are called equipotential is because the, if the dislocations get a favorable conditions, they can move through the paths defined by these equipotential lines, but the energy of these lines are different from one each other. And whenever the energy is lower down, the system energy, there is a gradient between the energy, the dislocation starts moving. It's a normal phenomena for electron, proton, or like electron and the atom. Atoms always move to the lower energy sides. We have seen in electronic configuration also, when electrons are at uppermost shell, they always try to go down to the lowermost shell or the ground state energy, because we always want to be in a ground state level. So similarly, when the dislocation, so as I said, just combining these two graphs, so if this is a line through which the dislocation is supposed to move, so this dislocation will move perpendicular to this equipotential line. So they will form like this structure, and then again, if they are moving in opposite negative pole as well, they will move like this following this structure. And depending upon how much energy they were provided, how much preferable sites they got, or how much temperature was risen, depending upon that factors, this circles will be defined. And why they are moving like this is because these are the more energy sites and these are the less energy sites. So they will always try to move from more energy sites to less energy sites, and then they were moving backwards. And this is how the dislocation movement is taking place. Also, these dislocations should have a minimum drift velocity, by which, or after gaining which, they can only move, because even if they are not having that much drag velocity or drift velocity, they cannot move. And that velocity can be provided if and only if they are exposed to the aging phenomena, or they are exposed with a high temperature environment or situation. So it's like that.
Okay, ma'am. Ma'am, so basically, if I get this right, the equipotential surfaces are basically like the probable places where the very solute atoms can move, like can be.
Dislocations are moving through this circles. Okay.
Yeah.
And equipotential lines are defining the lines or the path of the dislocation. So yeah, you can say that.
Yes. Okay, I got it. Thank you.
This movement comes under the Cottrell-Billby theorem. So first the equipotential lines were introduced using the interaction energy between dislocation and the solute atoms. But after that, when using the different energy gradient, the solute atoms were moved through the different energy gradients. So dislocation were moving perpendicular the direction where solute atoms were moving. That's why these perpendicular circles are again made. Also, there are a lot of circles made depending upon which favorable conditions they were given. It's like that.
Okay.
Any other thing? So this was in lecture 5, I think, Cottrell building. So before lecture 5, no doubt. If there is no doubt, I'll be happy because the topic was pretty much complex, and if you guys have understood, it's good. So this configuration will be called what? If that is a 7000 grade alloy of aluminium where zirconium is a constituent element. So zirconium and aluminium is bonded here, and will it be called clustering or will it be called long range, short range, atmosphere? Different terminologies were there na, in the week 2 lectures. So what you will call it? What is it? These blue atoms are aluminium and this green atoms are zirconium. What you'll call? Is it clustering or is it showing us any atmosphere, or what is atmosphere? What is clustering, or is it showing us any short range ordering, or is it random or ordered? What you feel? What is it?
It looks like some short range order.
Why?
If I notice carefully that AL is occupied on the FCCs, and the zirconium is making the corners. So it looks somewhat like a FCC lattice where zirconium is present on the corners. I'm just guessing.
So what is short range ordering? What did you understand? Short range ordering.
Basically, what I understood was that it's like for a small particular area, there is a repetition of atoms in a particular fashion. So that's what I got. There isn't clustering, it's more like there's no particular order seen.
Okay. So is it like if there are two atoms, aluminium and zirconium, if there are more number of bonds where the only green atoms are present, it will be called clustering. And when the preferable condition is giving us the result of green and blue atom combinations only, or more number of green and blue atoms combination rather than blue blue or green green, will it be called short range ordering?
Like if there are more of the interatom as compared to one atom, then I think it is short range ordering.
Yes.
But when it is lesser than, then it's clustering.
So it's like if it's Al and if this filled up is Al and this empty hole is zirconium. So if there is bonding between this, number of bonding or preferred bonding is this greater than this or this, that is short range ordering. And if the preferable condition is this, then that is clustering. Randomly it's taking place. Randomly the zirconium atoms are making bonds with each other and they are randomly arranged. So that is called clustering. But here it is short range ordering. Right? And when this type of short range ordering are long in chain and lot in number, then that will be called long range ordering. So is there any other terminology used to define this long range ordering?
It is super lattice.
Yes, yes. So it's called super lattice. So it's already written. It's the stacking faults. I have just put a picture of stacking faults so that you guys understand. If the ordering is CAB, 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 बीच में से अगर C गायब हो जाए तो ये CAB होना था, ये सॉरी CBA है, CBA है, इधर CBA तो है पर फिर C नहीं है, इधर पे C is missing, फिर BA रह गया. So due to that missing C, there will be creating a stacking fault, missing a site which is a preferential site for the solute atoms so to sit into. And this is the already I had shown compression and tension created inside the particular atom. So should I start from the starting, or Siddharth and Kapil, if you guys already also have a doubt? No doubt? Then I'll start from the starting of week
No
2.
doubts.
Okay. So you guys have gone through the lectures or you didn't? So you have understood all the things or you will go through the lecture after this? Okay, no problem. We'll start from week 2 lecture 1 to lecture 5. So in lecture 1, we got to know about, if you have any doubt in between, just stop me and let me know. So first the modifications were discussed. As I already said, the modifiers are attached to just change the site for the silicons to grow so that a long chain silicon will not grow, will not be formed inside the metal alloy, which can enhance the brittlity of with many times. So just to avoid that, we mix modifiers with the ALSI alloys mostly. Also, then we got to know about the wrought alloys a bit, which was already discussed in lecture week 1 series also. So from lecture 2, it's different than the previous topics, because from lecture 2, the solid solution hardening was started. So it's nothing like, as I said, if there is a particular atom, there will always be the dislocations present inside the atom, and that dislocations will always move or try to move, but our job will be to stop the dislocation movement by adding some solutes or adding some elements, constituent elements of a particular metal alloys. So we are doing that only using four techniques: elastic interaction, then modulus interaction, electrical interaction, and another one is stacking force. So in elastic interaction, we are just adding the solutes, and as we know, the solute size can be bigger or smaller. So bigger solute size will introduce some compressive stress, while smaller solute size will introduce some tensile stress inside the lattice. So can anyone of you tell me why this bigger size will introduce compressive and not tensile stress?
Basically, like when the bigger solid is like forcing itself in the already arranged fashion, so it's pushing the other nearby solute, other lattice particles away. So they want to come back to their original position by, so that's why it's compressive stress.
So for smaller solute size, if they are placing in an interstitial position or a substitutional position, the other atoms present surrounding that will try to make bond with it. So they will try to move close with that particular solute, but the other bonds which they are having will not allow them to make bond or get close to that solute, and there is a tensile force acting on that surrounding atoms, and due to which there is some strain introduced inside that lattice. So this is how the extra half plane, this symbol is indicating the extra half plane, which is introduced due to the solute atoms addition, and this extra half plane will restrict the dislocation movement until unless they are getting some preferential environment, some temperature rise or something. Then we can restrict the dislocation movement more and more by adding more and more solute percentage, as the graph was there where the stress strain graph. So it's like we are increasing the solute percentage. है ना? So the stress is increasing. So if there is more stress, so the dislocation have to have more energy to break this barrier of the stress, or this to break this stress barrier to move forward. So that's why if the solute percentage is more, the stress is more, and the dislocations will find it difficult to move inside the lattice. Then there were modulus interaction. The modulus interaction is also similar. So always remember, for edge dislocations, if the solute atoms are present, they will introduce this compressive, tensile and shear stress. But for screw dislocations, as I showed in one slide, there is a helical structure and spiral structure through which the dislocation will move. So for that reason, there will not be any compression or compressive or tensile stress. Rather, there will be the shear stress acting over there. So that is why the modulus or shear modulus is playing an important role in this process. So also, if the shear modulus, or not if, there will be difference in the shear modulus of the solute and the parent atom, and due to which the dislocations find it difficult. Also, due to the edge dislocation and addition of the solute atoms, the shear modulus decreases, and dislocations go towards the less shear modules. If they are always already present in the region which is having low shear modules, so dislocation will not find any other or safe or preferable site to move again. So that is why we are restricting that is how we are restricting the dislocation movement. After that, the fourth point was electrical. So again, due to the electronic configuration, the difference in electronic configurations, the solid atom will always introduce the dipole inside that particular metal alloy. The parent atom will have a particular type of electronic configuration, and the solid atom will have different. So due to this difference, due to this dipole, if the dislocation finds a positive end to feel preferable side to move, then solid atoms, if the solid atom is introducing some negative end, so then while moving through the lattice, if the negative ends and positive ends are, both the ends are present over there, the dislocations cannot move very freely. So we are disrupting the path. Third thing was stacking fault. So it's again a very interesting and important topic for further research, because this stacking fault is a unique phenomena. So it's like when there is a missing plane, everywhere you can find the stacking faults and you can restrict the dislocation movement. So due to the missing plane, there will be some disruption in the dislocation, and if anyhow the dislocation has been divided into two parts, so the Berger vector for each dislocation will be different, and due to which in between two divided the Berger vector there will be a place where the solid atoms generally feel safe or preferable to go and sit into it. So that stacking fault width is maintained. Thus, if the solid atom is sitting over there, and if it is maintained, dislocations will find it difficult to break down this barrier, this stacking fault barrier, to move forward. So these are the four techniques by which adding solid atoms we can restrict the growth, or we are restricting the path of the dislocation through which they generally move. After that, there were the techniques or some lattice interaction and uh, some phenomena which were discussed, which are like, again, as we have added the solid particles, so we can see it in a different way, like the solid atoms were restricting the dislocations. Anyhow, there will be some relation between the solid atoms and the dislocations. There will be always a stress and interacting factor uh, present over there between the solid atom and the dislocations. So if there is a bond, there will be a bond always between the solid atoms and the metal, parent metal. So as I have shown in this, so there can be clustering or there can be short range ordering. If this short range ordering is lot in number, so it will be like this. Not this. So so if it's like A B kind of thing, the things will be arranged like this at first stage. But if there is a dislocation movement due to some preferential side through this plane, so there will be some misalignments, and before, the opposite atoms were facing each other, but due to one step movement of the dislocation, this will be the next scenario where similar type of metals or atoms are facing each other. Always remember, if there are two types of metals, one is A, one is B is the solute atom, the energy of this thing will be always higher than this, the energy of the system. Okay, if the dislocations in its moving path facing this type of, sorry, facing this type of situation or environment, it will feel some barrier, but the barrier will be lesser than this case. In this case, the energy will be more. So this is how in this case the dislocation has moved. But in this case it will again find it difficult to move because similar type of atoms are facing each other. Also there will be repulsion force acting, you can say. But apart from that, this type of scenario is called the antiphase boundaries, because the anti-atoms or different or opposite type of atoms are facing each other. So anti-phase boundary also has its importance in this particular topic, because this anti-phase boundary will provide again a difficult scenario or situation for the dislocation to move further. So this is how we can say we are again disrupting the path of the dislocations. And also there was a formula of tau, where tau was defined as the strain or the stress acting between the dislocation where it is finding difficult to move further. Gamma is the antiphase boundary energy and T is the spacing. Antiphase boundary energy is higher this case, and this is why the stress needed to move the dislocation is higher, and this is why the dislocation need to break a lot of or more barriers in this case. So, solute atoms are always attracted towards the dislocation sites due to the interaction of their strain field, because as I said, there will be some strain field introduced inside the metal alloy due to the solute atom size or modulus or electrical or stacking faults. So, but the rate of the motion of these solute atoms will depend upon the diffusion rate. So diffusion is nothing but jumping of the solid atoms from one to the nearby vacant position. And this rate of motion of this diffusion, how they will move or jump into the nearby sites, and this is how they move from one place to another place just to catch up the dislocations, will depend upon the temperature and time as well. So it's a thermally activated phenomena. This is how this is why it's dependent upon the temperature that we are providing or the stress also externally we are providing. When the temperature is high, solute will quickly move towards the dislocation and second phase will be precipitated. So this second phase means if this is the dislocation, it's moving and the solute atom is jumping from one to another position. So what will happen is there will be a time when this dislocation moves very faster, when the temperature has increased. But there will be a time when this thing will accumulate before this and making some other type of microstructure, which will be a difficult site for the dislocation to break kind of this barrier. So if you see, there is a magnesium or Mg2Si precipitate. There also the precipitate restrict the dislocation movement in the 6000 series of wrought aluminum alloy. This is one example.
Excuse me, ma'am.
Yes.
Ma'am, one doubt regarding the APP. Ma'am, is the dislocation movement itself making the APP to form?
Yes. The
Also, ma'am,
dislocation is moving like you can imagine here. If this half plane is moving now in this direction, this was here for t equal to 0 and at t equal to 1 it is here. So if it is moving down, so now these atoms were facing each other, but now these atoms will be facing each other. So this is one example where all the atoms are similar, but where there is different bonding of AB, there will be the thing. Like, you understand?
yes, ma'am, but if the dislocation itself is causing this APP to form and it's difficult after that for the dislocation to move, can it be avoided? Like,
No, it's preferable. No, we want to disrupt the dislocation movement, and dislocation is giving us the chance by themselves that it's
To
moving
strengthen
and
it.
then making it difficult for themselves to move further.
Okay, so it's basically something which is, I mean, nothing which we have to do by like, you're not doing anything for it to happen. It's just happening.
It will happen.
Achha.
If the dislocation finds a preferable situation or environment, it will definitely move. And if somehow it's moving and creating this scenario, it will be difficult for them only to move further. What happens here? So then the solute precipitate will be there. If there is no solute precipitate, it can happen like the solute atoms has been accumulated somewhere, but they are not having enough attracting force with each other or bonded properly so that they can form the precipitate. But they are making just a clustered situation which is called atmosphere. So this atmosphere is again very important. Also, the mobility of the dislocation is equivalent to the motion of the dislocation. And we are just trying to restrict this mobility of the dislocation. Okay. And also trying to restrict the path of the dislocation so that it finds it difficult and it needs more stress or energy to break the barrier. Next is if the movement of the dislocation is away from the atmosphere, it will create another stress on solute because there is already established relation between the solute and the dislocation. Even if it is a stress and interacting stress, but still there is a relation between them. So as the dislocation further tries to break the barrier of the atmosphere and tries to move further and away from the atmosphere, there will be another stress acting on the solute. Solute will again try to catch up the dislocation or will try to restrict the movement of the dislocation. So it is a thermally activated process. So obviously if the temperature is increased, only then it can happen. Otherwise we'll just deal with the metal alloy which is having a precipitate, and that will be called a precipitate hardening. And unless until you are rising the temperature, the dislocation will not move further. There will be the equilibrium attained at that position. But if somehow the temperature has been increased or the externally stress is applied or some other environmental conditions or external forces are applied, the dislocation will again try to move forward. At that time, solute atoms jump from one to another position for their mobility, all because they will try to catch up the dislocations, and therefore solute atoms lag behind the dislocation because as I said, the dislocations will move with a very high velocity, but the solute atoms are jumping from one place to another place. First they are finding one vacant position nearby, then they are jumping, so obviously it will take more time than dislocation to move. And as the dislocation moves, there is an interaction stress which makes it difficult for the dislocation to continue their movement. As I said in previous case also, dislocation is moving, doing some stuff and making the situation more difficult for themselves only to move further. And the stress acting between this dislocation and the solute because of this away movement of the dislocation is a function of the journey of the dislocation. This interacting stress was the drag stress uh, when the dislocation moves and the solute is following them. When the velocity of the solute is very high and it's finding insufficient time to rearrange or for the solid atoms to get rearranged, in that condition solid atoms are considered as clusters, and or they will act as an obstacle to that dislocation. So it's a complex scenario, but if you imagine in that way that dislocation is moving and solid atom is trying to catch up, and then dislocation is making some other situation where it again finds it difficult to move farther, and in that time solid atom has moved and has achieved equilibrium position where it has come forward to dislocation, and the second phase precipitated or some clustering or the atmosphere is made, so it will be easier for you. Then there were some graphs which defines the how the temperature is interfering. So there, if this is stress and this is the velocity, this is time 1 and time 2, sorry, temperature 1 and temperature 2, and this will be the scene where temperature is helping the velocity to get more energized motion. Then after that, there was the ill point phenomena, which I have already discussed. The ill point is has been changed due to that movement of the dislocation and then falling the solid atoms. So yeah, should I ask question like the previous class?
Yes, ma'am.
Okay. Um, I need to see. So all the things I have already discussed, but again, whenever you discuss these things with someone else, na, it will be more clear to you. So yeah, so any one of you can just explain what is atmosphere? Siddharthan. So do you want to say anything about it? You are not audible. You are unmuted, but you are not audible. No, you are not audible. Hello. No. So Vanshika.
Ma'am, I think solute atoms are just like that. It's like atmosphere is like the buildup of solute atoms close to the dislocation, such that when the dislocation moves forward in the lattice, the solute atoms are somewhat attracted towards it and they follow back. And because the dislocations are moving at a rather faster pace as compared to the solute atmosphere, they experience a drag force backwards, the dislocations, which depends upon the velocity of the solute particles. Like the faster they move, the more is the drag force, and like after a particular
Hmm. Yeah.
yes, ma'am. After a particular point, if the velocity is so fast for the dislocations that the solute atmosphere can't catch up, probably, yeah, it would sort of, that's my guess that it won't be able to follow up.
Yeah, so there will be a bonding between the solid atoms, and but the bonding will not be that much, and there will be not much interaction and attraction between the solid atoms, so that they get bonded to get the second phase precipitated, but there will be they will look like cluster, and the atmosphere will be built up. It's called atmosphere, that is a built up solid atoms. It's fine. Then so there were a formula where it's calling in the last class that number of segregated solute atoms in a unit length of dislocation, NT, is equal to alpha n naught a d t by k t to the power 2 to the power half. So what it is really defining? What
Uh,
it is?
it's trying to say that the number of solute atoms on the unit length of the dislocation, like how they are segregated exactly.
And what are the depending factors on
Uh,
which?
the temperature, the time, the and the initial concentration of the what to say, like the solute atoms initially present in the volume.
And also, so it's like for aging, right? Temperature and time means at a higher temperature and we are holding it for a longer time means it's called aging. So what is
Yes.
preferable? How much time for aging is preferable?
Ma'am, like we had discussed that if you keep it for a few hours, then it's good, but for a few months also it is fine, like in the lecture.
Yeah. So generally for research purpose or for work, for our work, laboratory work, we just keep it for a few hours.
Okay, ma'am.
Next, as I already have discussed, the Cottrell-Wilby theorem. So why this what did you understand by diffusion? Diffusion.
It's the speed with which the solute atoms are able to move through the lattice, and it's time and temperature dependent.
Yes. Uh, can you brief me about the upper yield point and the lower yield point?
Yes, ma'am. Like I understood this that basically these solute atoms are always trying to pin down the dislocation. So when the process of this yield is onset, at that time that's at the higher upper yield point basically because a lot of stress is needed and because it's already very close to the dislocation. But as it goes forward, the yield point decreases because they're farther away. Basically, the velocity is going a little higher for the dislocations as compared to the solute atoms.
So in normal space-time graph also we can find this upper and lower yield point for steel also for any ductile material. So there is also another thing which is
Hmm.
related to this, that is called recovery. This is the same concept.
No, I didn't get that actually. Like recovery, I didn't get that correctly.
Oh, it's the same concept that how we are first what to say, we are first increasing the strain, increasing the stress, and after one point if the yield point is means we have gone beyond the yield point, it will start the recovery, means it will try to arrange themselves in such a way so that the stress, they can lower down the stress inside them, this dislocation movement and then solute atoms following them, these things, the same concept. And after that, after some certain time, the stress they cannot lower down further. So the stress, if we are increasing the stress, with increasing the external stress, the strain will increase. Before that, up to the lower yield point, they will try to minimize the stress even if we are inducing higher and higher strain. So that is mainly called recovery. Here also the same concept, na? The dislocation is moving, the solute atoms are following them, but after some times the solute atoms and the dislocations are arranged in such a way that the stress has been reduced for a certain time interval, and at that time, even if the strain is increasing, the stress is decreasing, and after few times, after a certain point, the strain is again increasing until unless it is going up to the fracture point or ultimate stress. So it's same. You will get to know about this recovery in a deeper way from in the subsequent lectures. It's also
Okay.
important where the reciprocal in a solid movement is more important. Okay, then what's it? So today you don't have any doubts, Siddhartha? I think your mic is not working. Have you gone through the lectures? Mm, so what did you understand by stacking faults? If I say what is stacking fault, not stacking fault interaction, what is stacking fault? No, Anshika?
No, I think it's like when there's an ordered arrangement of these lattice points in the lattice, and say it's like ABC, 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 and if I just remove one of those lattice points, then it will suddenly turn into some other lattice structure. So like that's a sort of a stacking fault. Basically, like in stacking fault effect, you have another small lattice uh, which is present inside a bigger lattice. So the dislocations can't move in that region where that stacking fault has occurred, and so the larger the width of the presence of that stacking fault, the more difficult it becomes for them to travel faster.
Yes. Hmm. And also, the missing of the one plane, it's not like it has to be the missing of all the similar planes. It can have, like as I showed here, one C plane is missing. That was an example that in FCC the arranged atoms are like ABC, and if the C is missing, it will be AB, more like an HCP lattice. But it's not like all the C atoms will be missing at a time. So it can have that only one plane is missing, and only there the stacking fault has been occurred. So
Yes, ma'am. Ma'am, this can be like one atom, like A, B, or A, B, C, then another C, and this can go for some more time.
sorry, I didn't understand.
Like, can it be like A, B, C, A, B, A, B, A, B, C?
Yeah, it can happen. It can be
Okay.
like a lot of C plane is missing for due to some defect, but it's not like all the C planes will be missing at time, because this missing is because of some defects, which is a sudden incident. So yeah, it's a common
Uh,
understanding.
Another doubt, like, doesn't this actually increase the energy of the lattice and makes it more unstable also?
Makes it more unstable is correct, but as there will be missing plane, so missing plane means it's not like the atoms will be missing. It can happen that have the atoms have been placed in some interstitial position, because if the atoms are missing, you can see there will be the stoichiometry will be disrupted now. It can happen that hundreds of atoms are missing, ऐसे अचानक से गायब हो गया, ये तो नहीं हो सकता ना. Means some phenomena has occurred, there is some defect due to which one plane is missing. Also this can happen that half of the plane is missing. C is there in the opposite side of the lattice, but the side we are seeing over here, the side which is facing the front, that is having the missing C plane. In the opposite side, the
Okay,
C
ma'am.
plane is present. So stacking fault is not like throughout the whole lattice the C plane will be missing. There will be stoichiometry defect then. Na?
Yes, ma'am. Understood.
Okay. Uh, any further doubt, or else I think we have discussed all the topics today already. There is no leftover topic. I thought today's session will be longer than previous session because today's topics are more complex. But I'm happy to see that you guys have understood. It's good. So I will share this slide with you all because the applications are also here. You can see the different applications of different alloys and yeah,
Excuse me, ma'am.
yes.
Ma'am, actually, there was a small request from my side. Ma'am, we learned those so many formulas for quadrant and Wilby theory, but like I don't know how to use it in a problem or so. Could you give me some examples of those problems where I can probably use it?
Okay, I'll find it out. I'll see if I get any problem
Yes,
regarding,
ma'am.
or if I met some problem regarding this quadratic theorem. But we'll see. Okay, in the next slides, I'll make some study material on Berger vector to more to understand it more properly in depth.
Yes, ma'am.
Yeah, and then some problems on this numericals, these formulas.
Sure, ma'am. This will be really helpful. Also, ma'am, for the exam point of view, should we go through the derivations often?
Uh, I'm not very sure about that because I'm not involved into that portion. But what I'd suggest that these formulas are not very difficult to remember because don't need to remember. You just remember the first formula that we are starting with, that the drift velocity is equal to diffusion coefficient by Boltzmann constant absolute temperature into the force. So this formula we are starting with, and then we are catching up with different steps in which we are introducing new factors. And this is how, if you practice once or twice, you'll remember all the because there are not lot of formula till now. We don't know about what other formulas are coming, but till now I think you can remember.
Yes, ma'am. Sure.
Will find it. If there are a lot of numerical, then it's important to remember these things. But if there is not much numerical, then it's okay. But I can't say that you don't remember because I don't know the exam things.
Sure, ma'am. I'll go through it once.
Okay. Then we can stop today's video. Okay. So thank you everyone. Thank you for going through all the topics, and this was a nice session interacting with you all. Thank you. We'll see you in the next Tuesday, 6 p.m. to 8 p.m. with our week 3 doubt clearing session. ठीक है? चलो.
Thank you, ma'am.
Bye. Good night.